Hello everyone, long time no see. It has been a while since I've uploaded either of my lectures on my YouTube channel named as Physiker. So here you are once again, where I would be demonstrating a lecture session on this specific day, which is a grandeur marking the 105th birth anniversary of Richard Feynman, one of the greatest physicists, living legendary physicist of all time, the greatest physics teacher of all time, to be more specific. And everyone knows quite very well that Richard Feynman was born on this day, 1918, and he pursued his BS from MIT, subsequently pursued his MS and PhD from Princeton University, and he was and exclusively into quantum field, where we are going to demonstrate certain notations over here, where I would be mentioning you people with the exact significance of a particular field for which Richard Feynman won the Nobel Prize in the year 1965. That was, you can see over here quite clearly, it's Feynman diagrams, where I would be demonstrating certain things which is going to be helpful for the sophomore and the high school students as well. So let's just get started, initiating with, so you can see over here with certain depictions, that is straight lines, we have to use certain conventions accordingly. Straight lines are going to represent the particles before and after the interaction, and the wavy lines are going to connect the straight lines and represent the particle exchange. So straight lines, you can say quite clearly, it's a very simple way of understanding things, and wavy lines are going to be generated just like this. So we are going to take certain epitomes in the forthcoming slides, which I would be showing it to you accordingly. The charge must be conserved at each junction, so obviously the conservation of charge needs to be followed, following the quantization of charge, which is quite familiar with each and every students, that is Q is equal to NE, is going to be followed. And the particle lines point in the same direction for both attraction and repulsion. So we also are going to denote the Coulomb's electrostatic force of attraction and repulsion between two fundamental particles, which we are going to take under consideration. The direction of the lines do not show the direction of the particles. So we are going to follow these notations accordingly. So you can see over here the electromagnetic interactions, which are being shown on the left hand side of this computer screen and the right hand side as well. So there is two electrons are interacting with respect to each one of them. That is, the instance is being shown before and after interaction. Gamma photon is being generated. There are exchange of particles which are taking place following Yukawa's meson theory. Most of the high school students and sophomore students are quite familiar with this particular term, that is Yukawa's meson theory. So mesons are going to be exchanged. These are going to be exchanged accordingly. So there would be an exchange of mesons accordingly, and after that you can see over here the electrons are going to get repelled due to Coulomb's electrostatic force of repulsion, which I have mentioned. So that's what Richard Feynman worked upon. It embarked upon the initiation of a new branch of physics named to be as quantum electrodynamics, for which he won the new Nobel Prize in Physics in the year 1965. So after undergoing electrostatic force of repulsion, so these electrons are moving away with respect to each one of them. Following with electron-proton attraction, where this electron and proton pair are going to undergo with Coulomb's electrostatic force of attraction, and once again there are going to be exchange in particles. So we already know why we are mentioning over here that's gamma. So let me tell it to most of you people who are unaware about the fact that gamma over here, it's a gamma photon which is being generated over here in this particular process, and we know that photons are nothing but the strong force carriers in the case of electromagnetic radiation, to be more specific. So Strong force carriers are going to be gluons in this case, and the electromagnetic force carriers are going to be exchanged in between accordingly. But upon subsequent deductions, we are going to deal with bosons, which are W and Z bosons accordingly, because certain particle emissions happens during weak decays, that is beta decays to be more specific, and it happens due to exchange of weak forces in nature and electromagnetic force in nature accordingly. So that's why I'm just trying to denote gamma radiation or gamma photons are being generated over here in this case. So once again, the electron and proton are being departed away with respect to each one of them in this particular screen, followed with beta minus decay. So maximum high school students are already aware about the fact about beta minus decay, where a neutron is going to get converted into proton with an emission of an electron. This is my electron having the symbol of E superscript minus, followed with the generation of antineutrino. So this is a reaction which takes place for either of the radioactive specimen, and the high school students as well as sophomore students are much more familiar with this particular particle reaction or nuclear reaction, to be more specific. So it's, you can see over here that what happens. I would just trying to denote the entire expression by the means of a Feynman diagram. So over here it's being mentioned quite very well. So it's a before, the post is being mentioned over here, and the pre of the reaction. So here comes a neutron, and there it generates a W minus boson. As I've already mentioned, that W minus boson is a carrier of weak force. And you can see over here electron and an antineutrino are being emitted during this process, followed with the generation of proton, means because you can see over here the neutron is getting directly converted into proton. So there itself it's being quite clear, and in the previous slide I was just trying to mention about the gamma photons. So they are nothing but electromagnetic force carriers, so which I didn't mention it to you previously. I was just trying to mention the interaction between electromagnetic force carriers and the strong force carriers, which are gluons. I was just trying to mention it. So anyways, over here in this case, so we can just try to mention it to be as electromagnetic force carriers. So why did Feynman deduce these? To have a better picture about the nuclear reactions which are taking place due to certain exchange of particles, and how the particles are getting converted into any other classical, means fermionic or bosonic particle. So we are not going to take consideration of either of the classical particles over here. So once again comes beta plus decay. It's quite clear now the proton needs to be converted into neutrons. So here comes the reaction which the high school students who are preparing for even certain Olympiads and JEE advanced examinations are also going to be familiar with this specific reaction. So that's why I already mentioned that this lecture session is going to be made for both sophomore and the high school students. So over here what's being mentioned, the proton is getting converted into neutron along with the emission of the anti-particle of electron named to be as positron. So positron is going to be emitted accordingly, along with the generation of, you can see over here, this is neutrino. So there are several such reactions which are going to take place accordingly. So this is how it happens and how the reaction takes place. So that's the most important thing. So you can see over here, once again, it's the pre of the reaction. So before pre of the event, the pre-situation of the event is being mentioned over here, where the proton tries to move, and there itself it generates W plus boson. Once again, W plus boson is the carrier of weak force. Once again, it's a carrier of the weak force. So I will write it down, carrier of weak force, and is a 5th generation particle. So W plus boson, and there itself it generates positron and neutrino accordingly. That's what I mentioned it over here. With, you can see over here, with getting converted into a neutron. So that's how the reaction takes place. So you can see over here, you can just try to read the statements which I have formulated over here while getting compacted into a single sentence at the bottom of this particular slide. So there itself, everything is going to be quite clear to each and every one of them. So there itself, you can see over here, moving forward. So now the electron capture, this is also one of the most interesting phenomena which takes place in the case of either of the radioactive emissions. So this is also a property exhibited by either of the radioactive specimen, a radioactive element. So over here, the proton and electron combines to produce neutron and neutrino. So once again, this reaction is going to be mentioned over here. So proton and electron, they are going to undergo Coulomb's electrostatic force of attraction. So I can write it down, Fc attraction over here in this case, and there would be exchange of particles once again, which is going to take place following Yukawa's meson theory. The W plus boson is going to be transferred, and there itself the generation of neutron and neutrino would be taking place, and they would be following a trajectory while getting deviated away with respect to each one of them, just like the way it's being shown over here. So that's what it's being pushed on. Proton turns into a neutron by trapping an electron. The exchange particle W plus leaves a neutrino after the reaction. So that's what I was just trying to mention. So Feynman, Richard Feynman, just made particle physics look like a piece of cake. It's true. That's what I would be mentioning. So this is how I am just trying to render a tribute on this grandeur of 105th birth anniversary of Richard Feynman. So over here, once again, we have electron proton collision. So you must be thinking, like, how can an electron and proton collide with respect to each one of them? So it's an obvious thing. So we have to make that Coulomb's electrostatic force of attraction get dwindled in this case. So that's what it happens. This is what happens. We have to create a specific condition. That's what which happens inside of LHC. Everyone might have heard about the name LHC, that's Large Hadron Collider. It happens inside of either of the particle accelerator. So that's what it's being depicted over here when proton electron is being compelled to overcome Coulomb's electrostatic force of attraction. It forms neutron and neutrino. So there itself, once again over here, you can see over here the arrow, the direction, that's what it was already being mentioned previously in the very first slide, that the waves which are being generated over here, it's going to denote the exchange of the particles. So over here, the arrow denotes where the W minus boson is being transferred. So proton, electron, there itself the pre part of the event, and after that neutron and neutrino are being generated while getting departed away from each one of them. So they're moving away. In fact, you can say there might have been certain sort of collisions might have taken place, who knows, but we cannot just try to depict it accordingly, because we already know one fact, that internal forces are not going to result into any impact to the rate of change of momentum. So there itself, I can just try to mention this in terms of classical mechanics point of view. So let's move forward to demonstrate certain more things. So neutron collision. So once again, just the reverse of this reaction, the reaction which was being mentioned over here. I'm just trying to perform a reversible type of particle reaction, so where they are going to form a proton and an electron pair accordingly. So once again it's being depicted over here for a neutrino and a neutron collision. So once again you can see our W plus boson gets generated, that too in the reverse direction. So one thing is quite clear, so you must be knowing the direction. What's about this direction, by the way? They have mentioned the direction, so where this W plus or W minus bosons are being directed. So that's the one of the most important things, one of the most important phenomena which I would try to mention over here. So that's nothing but the time arrow. They are just trying to mention the time arrow. So we know that this is, I will just try to mention it in all the diagrams. I could have mentioned it, but let me try to mention it over here in this specific diagram, because I'm just trying to demonstrate this specific phenomenon over here. So this is the arrow, and here we are present to future, and on the back side of it I can make it to be as past. So this is how the event is taking place. So W plus boson is the exchange of particle is moving towards the past side. That means against the flow of time. So that's what, it's one of the most bizarre phenomenon. So that's what it says. So that's what it's just trying to justify, that tachyons can move faster than the speed of light. So by the means of Feynman diagrams, it was being proven and justified theoretically. So we'll discuss furthermore someday for sure, that is in my forthcoming lecture sessions over here on my YouTube channel Physiker. So stay tuned actually, my friends. So we are having some more contents to be delivered to you. So now we are having antineutrino proton collisions. So proton and antineutron neutrino are going to act with respect to each one of them to form neutron and a positron. So the particles you can see over here, the Feynman diagram for this particular event is being depicted over here. The proton, and there itself we are having an antineutrino. They are about to interact with respect to each one of them while exchanging W plus bosons, you can see over here. And that's what you can see now over here. The W plus boson tries to move along the direction of the flow of time, and there itself neutron and positron pairs are being produced as a result of that. So this is how it happens, and the final one you can see where the exchange particle W minus boson leaves a positron after the reaction. So before just trying to perform the significance rendering for annihilation, I would like to mention you one thing over here about the standard particle chart, that particles are of two types for a better understanding of the concept. So one particle would be referred to be as force carriers, another set of particle would be referred to be as matter builders. So force carriers are going to be for all the four type of forces, starting with gravity, electromagnetic, EM, that's what the abbreviation which I am just trying to make it over here, followed with strong, and last but not the least weak. So what are the particles which are involved into the carrying of these aforementioned forces at the bottom? So starting with gravity, if you are going to say, so it's still a hypothesis that we are having a certain set of particles called gravitons. For electromagnetic, which I already mentioned during the initiation of this lecture session, that EM, electromagnetic forces, are going to be carried out by the means of photons. For strong, I've already mentioned it to be as gluons. So this is what the quantum electrodynamics embarked upon, the initiation of the unification of these forces, you can say. So I will mention it to you, by the way. Strong forces for gluons, and weak forces we are going to have W and Z bosons. and W would be classified into W plus and W minus, which you have already seen in the aforementioned nuclear or particle reactions. So we are just trying to unify all the four forces of nature. That's what the prime motto of theoretical physicists, which they have been doing, and computational physicists as well. So they have been just trying to unify all the four forces of nature. So there are several ways they are just trying to make it perform by certain ways. But I would like to mention you one thing, that is the EM force, the electromagnetic force and strong forces can be unified, and they have been unified by the means of a specific branch which got paved by the basis of this particular branch discovered by Richard Feynman, which is quantum electrodynamics. So the branch is named as your quantum chromodynamics. Similarly, EM electromagnetic force has been unified by the weak forces of nature in a specific branch named as electroweak theory. I will write it down over here, electroweak theory. So this is how everything happens. You can just try to imagine the situations accordingly. So now challenges, EM strong and weak forces, they have already been unified, but it's proving out to be difficult for the unification of these three forces with the very first force, which is the weakest force in reality, named as gravity. So that's the challenge for all the theoretical and computational physicists of this era. So let's move forward. So annihilation, it's quite clear that its annihilation means complete destruction. So when an antiparticle set is created, it can be observed, but only for a very few short time, and the short time is going to be of the order of 10 to the power minus 18 seconds. So that is your attoseconds. So any particle would be persisting for attoseconds, and after that it would be annihilated. So that's how everything came into existence, by the means of annihilation, subsequent annihilation just after the Big Bang explosion. So it will soon collide against its particle, and they will be destroying each other, and yes, they have to follow the conservation of energy and mass accordingly. So that's why it's being mentioned. You can see over here we are having an electron and we are having a positron on the other side of it. So we are just trying to make it interact with respect to each one of them, and they interact, and there itself they generate gamma photons, and these photons are going to be in the form of spark, and that's how you can think about imagination, like they're just interacting, and kaboom, there itself they get completely annihilated with respect to each one of them. So leaning towards the forward direction, so I would like to mention this is how the reaction, it's all about. Electron and positron, they would be interacting to produce a gamma photon, which is observable with the means, by the means of a spark. That's what spark means. Photon, it's going to be visible in this case, and sometimes it's not going to be visible in this case. So gamma photons cannot be observed by the means of human eye. So that's the reason whenever an electron and positron, they have been continuously, interminably, they have been interacting with respect to each one of them, producing a number of sparks which cannot be observed by our human eyes. But if it would have been generated, if it would have been generating a visible region photon, then I believe that the human eyes would have comprehend those reactions accordingly. So that's what it's being mentioned over here. So conservation of momentum, conservation of charge, conservation of mass, conservation of energy, all these conservation of the state variables are going to take place accordingly. So let's move forward, and in a similar way pair production can also be explained over here. Once again, we are having a positron and an electron. When they are going to, you can see over here a high energy photon like a gamma ray can vanish to form a pair particle, an antiparticle. They would be producing this, just the reverse of this, of the previous reaction which we had observed over here. A gamma photon can generate this pair, and this pair of matter and antimatter, that is referred to be as your proton, not the proton actually, means having the significance of a proton, which is your positron, and an electron accordingly. So this is what it's being mentioned over here. So this is how it can be. Once again, we can use Feynman diagram to represent all these accordingly. All these diagrams for a better significance of understanding of particle physics. And this is what happened during Big Bang. This is what happened during Big Bang explosion. This is what happened just after and before accordingly. So this is how it's for today's lecture session on this 105th birth anniversary of Richard Phillips Feynman, and I hope that you people are going to like this lecture session accordingly. Looking forward to post certain more interesting facts about certain branch of physical sciences, so you can comment accordingly on the bottom of the comment section. So that's what I would be looking forward for each and every students of mine, especially from certain nations. So that's it for today. Thank you very much. Stay tuned, stay focused. A very good night on this occasion. So it's Avinav Banerjee for you, an absolute Physiker. We'll be back once again on the very next occasion of the birthday or birth anniversary, or let's say some certain event which is quite significant in the field of science. Would be demonstrating a lecture session once again on a specific topic, but if you are going to mention it in the comment section, I would be definitely demonstrating and delivering a lecture on that specific topic of physical science. Thank you very much.